Hello again, and welcome to our first of 4 lectures on solving systems of linear equations and matrices. In today's lecture, we'll look at 2 equations and 2 unknowns, and then we'll extend it to larger systems of equations. And we'll ask questions like this. What do the solutions look like? How many solutions can a linear system have? And then we'll represent these systems using something called matrices, which will help us in making the system more concise in our minds. In the subsequent lectures, we'll study these matrices a bit more, and we'll see that they have a lot more uses than just solving linear systems. So let's begin, as I always like to do, with a simple example of a linear system. And let's consider these following 2 equations in 2 unknowns. The first equation is x plus y equals 4. The second equation is x minus y equals 2. So here's the game. What are the values of x and y that satisfy both equations simultaneously? So we're trying to find x and y. We have what we say, 2 equations, 2 unknowns. Now, these are called linear equations because those variables x and y occur to the first power. You don't see anybody squared here. You don't see square roots. You don't see trigonometric functions, etc. It's just the variables to the first power. Now, there are lots of ways of solving such systems. You might notice right away that if you were to add these 2 equations together, you would immediately eliminate the y variable, wouldn't you? And you would have 2x equals 6, which means x is 3, and then using that value, you could find the y value. Or you could do what we like to call method of substitution, which I'll show you in a minute. But the third method, the most important method, Gaussian elimination, has the advantage that it works for large systems. I mean, this is a pretty simple problem, 2 equations, 2 unknowns. But imagine trying to do this manipulation of adding equations if you had 50 equations and 50 unknowns. Fortunately, Gaussian elimination will solve even systems that big. So let's first look at what I like to call substitution. And this is a very popular way when you don't have too many equations and too many unknowns. From the first equation, x plus y equals 4, you can solve for one of the variables. Say y equals 4 minus x. And then take that value of y and plug it into the second equation. So that equation was x minus y equals 2. Putting in this new value of y, we get x minus the quantity, 4 minus x. Notice we've eliminated the y variable completely. That equals 2. Combining some of the terms here, 2x equals 6, and hence x is 3. And once you know the x value from that equation involving y equals 4 minus x, you obtain y equals 4 minus 3, or 1. So our solution, our unique solution, is x equals 3 and y equals 1. And that's often written as an ordered pair, the pair 3, 1. X is 3 and y is 1. And I invite you to check your answer in the original system. You'll see that x equals 3 and y equals 1 satisfies both equations. But now let me show you Gaussian elimination. It'll be fairly simple in this example. Here's the idea. You start with the system, x plus y equals 4 and x minus y equals 2. And using that x in the upper left-hand corner, we will eliminate the x right down below it. And the way we'll do it is as follows. We'll multiply that top equation by minus 1 in this case, and add it to the second equation, and that will produce a new second equation. So here we go. First of all, rewrite the first equation, x plus y equals 4. Now multiply that first equation by minus 1 and add it to the second equation. Hence, the x's are eliminated. And minus 1 times y in the first equation, minus y in the second equation, leaves a minus 2y. And then minus 1 times 4 plus 2 is minus 2. So the second equation has changed. It's now minus 2y equals minus 2. You see how that works? It's kind of complicated arithmetic even in this simple example. Well, now we have a pretty nice second equation. We can divide both sides by -2 and we get y equals 1 for our second equation. And knowing that y equals 1, you can go up and plug that into the first equation. Y is 1 and then x is 4 minus y, or 4 minus 1 or 3. We obtain the same answer we had before. So that's Gaussian elimination in a very simple setting. Let's take it up a notch. Let me show you a 3x3 system. Now we have 3 equations. They're linear again, if you notice. All the variables occur to the first power. It's 3 equations, 3 unknowns, which I will call x, y, and z. In practice, you can use any letters you want for the unknowns. Oftentimes, you'll have subscripts like x sub 1, x sub 2, and x sub 3. But here we'll just use x, y, and z in this example. So there you see the 3 equations. The first one being x minus 2y plus 3z equals 9. And using that equation, I will eliminate the x's in the second and third equations. So you start in the upper left-hand corner, and using the x variable up there, take a suitable multiple of that first equation, add it to the second equation, eliminating the minus x in the second equation. Here we go. All right. Again, lots of arithmetic. Okay, we have the equations. Rewrite the first equation, and now take a certain multiple of the first and add it to the second. Well, this is not too hard, is it? It's actually 1 times the first equation added to the second equation, or if you want to say it in simpler language, add them together. So the x's are killed off. Minus 2y plus 3y leaves y. 3 minus 2 is 1. And then 3z plus z gives 4z. And then on the right-hand side, the constant terms, we have 9 minus 2 is 7. So I have a new second equation. There it is, and notice the x has been eliminated from it. All right, now we look at that third equation, and we see the 2x over there. We want to get rid of it. So I'll multiply the first equation by an appropriate constant to eliminate that 2x. What should I multiply it by? Yeah, by minus 2. So minus 2 times the first equation added to the third equation yields a new third equation. Here we go. Let's do the arithmetic. Minus 2x plus 2x, goodbye x. Minus 2 times minus 2y is 4y, minus 5y leaves minus y. And now let's do the z's. Minus 2 times 3z is minus 6z plus 5z. That leaves minus z. The right-hand side, minus 2 times 9 is minus 18 plus 17 is minus 1. Whew. A lot of arithmetic. But look what we have here. This is a much better looking system than we started with. The x's have been eliminated in the second and third equations. Okay, what do you think we do now? Right, we step over, and using that second equation and its y value, we eliminate below y. In other words, that third equation has a minus y in it. I want to get rid of that minus y in the third equation. So I multiply the second equation by a suitable constant and add it to the third equation. Again, it's pretty easy here, isn't it? Just multiply the second equation by 1. It's basically unchanged. So here we go. We're adding the second equation to the third equation, producing a new third equation. All right, here we go. Y plus minus y, bye-bye y. 4z minus z is 3z, and 7 minus 1 is 6. So we copy the first equation over. We have the same second equation, but now my third equation has only one variable, just z. Look how simple this system is now. This is a really good-looking system in that it's got everybody sort of swept away below the x's and y's. It's kind of what we like to call upper triangular, isn't it? Now we can do one more simplification. We can divide the third equation by 3, and then we immediately know what z is. Z is 2. Okay, and given the value of z, you can now work your way back up. This is often called back substitution. Meaning, starting with the bottom equation, z equals 2, you can determine y. Y plus 4 times 2, because z is 2, equals 7, so that makes y equal to minus 1. And now go up to the top, and you have the x variable determined by the equation x minus 2 times the y value, minus 1, plus 3 times the z value, 2. That's supposed to be equal to 9. Do the arithmetic, you get x to be 1. Whew. I'm tired of that. That was a tough problem. Lots of arithmetic, lots of multiplying one equation and adding it to another equation, but we've arrived at a unique solution. X is 1, y is minus 1, z is 2. And again, that can be written as a ordered triple, 1, minus 1, 2. If you go back and check those values, you'll discover that they satisfy all three of the original linear equations. So we got the right answer. Okay, let me make some comments about this process called Gaussian elimination. As I've said many times, there's a lot of arithmetic. And fortunately, computers and even your graphing calculators have built-in programs to do basically what we just did by hand. They're able to solve linear systems very effectively, and the algorithm they use inside these machines is pretty much what we just illustrated in that example. This technique of Gaussian elimination works for any number of equations and any number of unknowns. You can have big systems. In applications, I've seen systems of 1,000 equations and 1,000 unknowns. That's routinely solved by computers. So here's the next question I'd like to ask. You're given a linear system of equations. You have some equations in front of you. What kind of solutions can you expect? How many solutions does a linear system have? In that previous example and in the first example, we had a unique solution, didn't we? That system gave rise to one solution. Well, let's explore this a little bit more. And I'd like to explore it through some simple examples, but these simple examples illustrate the final result. Okay, so here's our next example. It's a very simple example. It's two equations, two unknowns. 2x minus y equals 3, minus 4x plus 2y equals 6. Okay, two equations, two unknowns. Here's the game. Find x, find y, such that both equations are satisfied. Here we go, Gaussian elimination. Starting with the 2x in the upper left corner, I'd like to get rid of that minus 4x below it. So I multiply the top equation by an appropriate constant. What constant should that be? Multiply it by 2 and add it to the second equation. So when I do that, the x's disappear, 4x minus 4x. 2 times minus y is minus 2y plus 2y, or 0. Uh-oh. Not only did the x's get eliminated, but so did the y's. How about the right-hand side? 2 times 3 is 6 plus 6, 12. And we've arrived at a new system equivalent to the old system. And look at that second equation. 0 equals 12. That's never true. 0 is not equal to 12. What's our conclusion? This system has no solution. And the big word for that is inconsistent. It's a system of equations for which there's no solution. Let me show you the geometry of this system, and you'll see why there's no solution. In this simple case, each equation represents graphically a straight line in the plane. One of the equations was 2x minus y equals 3, and if you put that in slope-intercept form, you get y equals 2x minus 3. The other equation was minus 4x plus 2y equals 6, and in slope-intercept form, that reduces to y equals 2x plus 3. Well, what do you notice about these two lines? They have the same slope, the slope's 2, but they have different y-intercepts, don't they? One of them is minus 3, one of them is plus 3. In other words, these are parallel lines. They don't intersect, and hence there's no solution. There's no common point on these two lines. Let's move to a second example. the same first equation, 2x minus y equals 3, but the second equation now is x plus 2y equals 4. Now here's a case where I'd like to avoid fraction land. You could multiply the first equation by minus a half and then add it to the second equation, and that would eliminate the x in the second equation. But if you're like me, fractions are not your best friends. And one way to avoid fractions in this problem is to flip the two equations before you start working. So let's write them in reverse order. X plus 2y equals 4 becomes the first equation, and 2x minus y equals 3 becomes the second equation. And now it's easier to eliminate below that x. Multiply the first equation by minus 2, add it to the second equation, goodbye x. Minus 2 times 2y is minus 4y, minus y is minus 5y, and minus 2 times 4 is minus 8 plus 3 is minus 5. So I have a new second equation, and now I can divide by minus 5 and get y equals 1. And knowing what y is, you can plug that into either equation, and you'll discover that x is 2. So the solution to this system is pretty nice. There's one solution, x equals 2, y equals 1. Here's the geometry of this situation. That first equation is the same line we had before, y equals 2x minus 3, but the second equation, x plus 2y equals 4, if you do it in slope-intercept form, it comes out to be y equals minus x over 2 plus 2. And these two lines have different slopes, and hence they're going to intersect. And they intersect in the point 2, 1. So, a unique solution. Let's go to perhaps the most complicated of these three cases, and that's illustrated in the following example. Our first equation will be 2x minus y equals 3, and our second equation will be minus 4x plus 2y equals minus 6. So there are our two equations. Two equations, two unknowns. Let's solve them. All right, I want to eliminate the minus 4x in the second equation, multiply the first equation by 2, and add it to the second equation. There goes the x term. 2 times minus y in the first equation, added to the second equation, eliminates y also. Uh-oh, we've gotten rid of both x and y, but watch what happens to the right-hand side. 2 times 3 is 6 plus minus 6. The right-hand side evaporates also. And our second equation is a pretty dull equation. 0 equals 0. In fact, you can just eliminate that equation, can't you? It gives you no information. What's going on here? What's happening here? Does this system have solutions? Well, yeah, it has actually an infinite number of solutions. For any y value, you could plug that in, and that would generate an x value on the line 2x minus y equals 3. And here's how you write this the more complicated case where you have an infinite number of solutions. Let me say there are lots of ways of writing it, and people, especially students, sometimes don't write it the same way. But in textbooks, here's how they usually write it. They take the x variable and try to get it in terms of y. So 2x equals y plus 3, divide by 2, x is y plus 3 over 2. So think of it this way. For any y value, you plug that in, and that generates an x value. And that xy pair works. That xy pair is a solution to the original system. And sometimes they'll even say, okay, let y be any real number, call it a. And if y is a, then x is determined. X is a plus 3 over 2. And that's a very common way of illustrating that there's an infinite number of solutions. For every real number a, you generate a solution. What's the geometry of this case we just looked at? What's the relationship between that first equation, which is a straight line, and the second equation, which is also a straight line? Well, they're on top of each other. It's the same line. Both lines are y equals 2x minus 3. That's why there's an infinite number of solutions. Any point on that line solves both equations. So here's the moral of the story. These simple cases illustrate the big theorem here, that given a system of linear equations, I don't care how many equations there are and how many unknowns there are, only three things can happen. Either there's no solution, exactly one solution, or an infinite number of solutions. In particular, given a linear system, you'll never have exactly 7 solutions, or 14 solutions, or 2 solutions. It's either 0, 1, infinity. That's always going to be true, one of those three cases. Okay, now we mentioned that matrices will play a role in these lectures. Let me show you one way to use matrices right away to simplify the notation for linear systems. Now, a matrix, I'll formally define it next lecture, but I think you know what it is. It's an array of numbers. It could be square, or rectangular array. It has rows of numbers and columns of numbers. And given a linear system, you can express that system using a matrix notation, and it's a very simple way to do it. Let me show you an example. Here's the linear system. It's 3 equations, 2 unknowns. The first equation is x minus 2y equals 5. Second equation is 2x plus 3y equals 3. And the third equation is 3x plus y equals 8. The game would be, as usual, solve that system. And we could do our Gaussian elimination steps, as we've done before, and in a minute we'll do it. But let me first show you how you express that system as a matrix. Okay, the coefficients of the left-hand side, where the variables are 1 and minus 2, and the right-hand side is 5. Those form the first row of our matrix, 1, minus 2, 5. Then we have a second row of the matrix, which comes from the second equation. The coefficients are 2, 3, and the right-hand side is 3, so the matrix is 2, 3, 3. And the third equation, I think you get the picture, is 3, 1, 8, because 3 is the coefficient of x, 1's the coefficient of y, and 8 is the constant term on the right-hand side. So that matrix is kind of a concise way of expressing the linear system without having all those variables in there. We're sort of saving some chalk here, aren't we? And by the way, if you use a graphing utility, you have to express your linear system using matrices. So it's pretty important to do it this way. All right, let's do the Gaussian elimination steps and do them simultaneously with the matrix representation. All right, what would the first step be over there with the system? Well, to eliminate the 2x in the second equation, I'd multiply the first equation by minus 2 and add it to the second equation. So I would get minus 2 times x plus 2x, ideos x, minus 2 times minus 2y is 4y plus 3y is 7y, and the constant term minus 2 times 5 is minus 10 plus 3 is minus 7. Now look over there at the matrix. You do exactly the same thing to the matrix that you just did to the equations. Multiply the first row of the matrix by minus 2 and add it to the second row of the matrix. Watch what happens. Minus 2 times 1 is minus 2 plus 2, 0. That corresponds to having eliminated the x. Minus 2 times minus 2 is 4 plus 3 is 7. And then over there on the right, minus 2 times 5 is minus 10 plus 3 is minus 7. See how that worked? It's kind of neat, isn't it? The matrix now corresponds to the result of the first step of Gaussian elimination. Well, you do the next step. I'll do it a little bit quicker now. Minus 3 times the first equation added to the third equation. That gets rid of the x. Minus 3 times minus 2 is 6 plus 1 is 7y. Minus 3 times 5 is minus 15 plus 8 is minus 7. If you do those same steps to that matrix, you'll obtain in the bottom row 0, 7, minus 7, which precisely corresponds to the latest version of our linear system. Well, now what could you do? What would be the next step? Well, notice that the third and second equations are precisely the same. So you could add, say, minus 1 times the second added to the third. That eliminates the third equation. And you also could divide the second equation by 7. And so now our new system using variables is x minus 2y equals 5 and y equals minus 1. And then the trivial equation 0 equals 0. And over there in the matrix notation, you see that it precisely corresponds. Now, we could do that so-called back substitution here, couldn't we? Knowing the y value, you could find the x value. But let me show you one more step that a lot of calculators do automatically. I can get rid of the y term in the first equation using the second equation. In a sense, I'm going backwards now. Watch how I do it. Multiply that second equation, y equals minus 1, by 2. So 2y, and add it to the first equation. That'll eliminate the y in the first equation, and 2 times minus 1, the right-hand side, is minus 2 plus 5 is 3. So now we have a sweet linear system. Look what it looks like. X equals 3, y equals minus 1. What's the solution to that system? It's staring at us. X is 3, y is minus 1. Now look over at the matrix. The matrix, if you read it the right way, the first equation translates x equals 3, and the second equation translates y equals minus 1. Isn't that neat? And again, these matrices are really, really valuable in expressing a linear system, mainly because you don't have to keep copying those letters down, the x's, y's, and z's. And second of all, if you're using a graphing utility or a computer, this is what you have to do. Now, a little study tip here. If you look in textbooks that cover what we call linear algebra, that's what we're studying right now, solving linear equations, you'll notice that some books like to put a vertical line in the matrix over there on the right-hand side to distinguish between the coefficients of the equations and the constant terms on the right-hand side. In that previous problem, the right-hand side was 5, 3, and 8 in each equation. And sometimes a vertical line lets you see clearly which part of that are the coefficients and which part are the right-hand side, the constant terms. It's not necessary to do that, but a lot of books prefer to do that. So let me summarize Gaussian elimination as it goes both with equations or the corresponding version with those matrices. What are the operations that we're allowed to do? Well, we can interchange 2 rows, meaning interchange 2 equations. And we did that in a previous example. That often makes for a better x term to eliminate below. You can also multiply a row by a non-zero constant. For instance, you might want to divide both sides by 7, and that's a legal operation. But the most important operation, the one that is most complicated, is adding a multiple of one row to another row. But those 3 steps are the heart of what we call Gaussian elimination. Doing those 3 steps, you can take a linear system and ultimately find out whether or not it has solutions and what kinds of solutions it has. Okay, let's do some simple questions here to see how we did today in this lecture full of lots of arithmetic. Suppose I were to give you a matrix and ask you, what's the corresponding linear system represented by that matrix? And I'm not going to use that vertical line notation, so it's a little bit trickier problem. Suppose I said the following. The matrix is a 3 by 3 matrix, meaning it has 3 rows and 3 columns, and the numbers are 1, 1, 2 in the first row, 2, minus 1, 3, and then 3, 3, 5. I claim that that could be interpreted as the matrix of a linear system of equations. What's the corresponding linear system? Well, the first row would be the first equation. And if we're using, say, x and y as our variables, it would be x plus y equals 2. That third column is the right-hand side. It consists of the constants. What about the second row of the matrix? What does that correspond to in terms of equations? Right, 2x minus y equals 3, and then the third one is 3x plus 3y equals 5. Okay, good going. That was, I think, a somewhat difficult lecture because of the complicated arithmetic involved. And in our workbook, we'll have some examples where you can try to do this Gaussian elimination on your own. Take your time, check your arithmetic, because there's lots of multiplications and additions involved. Next lecture, I'd like to turn to those matrices that we just used, and we'll apply them to other scenarios. We'll discover that matrices are not just useful for solving linear systems. So, I'll see you next time when we continue our study of systems of linear equations and matrices.